last time of the dreaded determinant of the differential operator. So we had d phi star, e to the minus I, integral d4x, phi star, differential operator of phi equals some normalization over the determinant of the differential operator. That's about as scary as you can get. But we made sense of it. We took the Lagrangian, which was d mu phi. So this guy's starred, which after integrating by parts, we did phi star d mu phi. There's our differential operator. And we then had 1 over the determinant of d mu. Okay, d, just to be sure, has this background field in it. D mu is d mu plus I-E a mu. So here's our background field. And we wrote this as e to the minus trace log of d mu. Then we expanded the log and ended up as some number e to the minus integral d4x x log d mu. It's just starting to look a little bit more familiar. And then ended up with integral d for x. No, sorry, I need this in the exponent, so let's do exponent minus integral d for x with e squared f mu nu of x delta squared of x minus y. There's another d4y here, f mu nu at y, and number-wise there was 4d minus 1. So that's starting to look like something familiar. And so now we're just going to complete the exercise.
What's little b? So it's 4.
Is there a question? No. Okay. So I want to evaluate del squared of x minus y. And in a way, I told you how to do it, but I was going fast at the time last time. So I just used words and didn't actually do this. Now, we have integral representations for delta of x minus y. But let's look at what happens when we do delta squared. So I'm going to Fourier transform it. And let me just call the Fourier transform d2 of q. Is the integral d4x e to the, let's make it plus I q dot x of delta squared of x. Okay, it's just a function of x minus y, so I'm just putting an x here. Okay. Well, this is integral d4x e to the I q dot x. Basically, this turns it into a usual Feynman integral. So d4k 2 pi to the 4th e to the minus I k dot x over k squared. And then there's e to the minus I, then there's another integral, so d4 L over 2 pi to the fourth. L dot x over L squared plus I epsilon. Okay, at this stage, the Fourier transform gets done. It just sets Q is equal to K minus L as a delta function. So I get rid of one of the integrations, and let's make it the following: d4L, 2 pi to the fourth. There's a 1 over L squared plus I epsilon, and there's a 1 over Q minus L squared plus I epsilon. So this is just the scalar bubble loop. This is just what you get when you do two propagators. So it's a very simple thing to evaluate. It is then minus I over 16 pi squared. I'm doing dimensional regularization, so 2 over 4 minus d plus gamma minus gamma plus log 4 pi, if I got my signs right, minus log q squared over mu squared Okay, so there's that. So the only q dependence sits in the log. Now, to get delta 2 back, then delta squared of x minus y, so is then the reverse Fourier transform. You take e to the d4q over 2 pi to the fourth, e to the minus I q dot x minus y of this thing that I just calculated, d2 of q. And that the first piece is just constant, so that the Fourier transform of the constant is a delta function. So I get a delta function of x minus y. So let's just write it as 1 over 16 pi. I'll just write this as 1 over epsilon bar is all those constants sitting there. Epsilon is the 4 minus d over 2. Delta 4 of x minus y. And then the other piece I'll just keep as minus I over 16 pi squared L of x minus y. It's the Fourier transform of the log. So this is just integral d4q 2 pi to the fourth e to the minus I q dot x minus y of log q squared. Okay. So the noteworthy thing is that the divergences are local. That's a good thing. That's just the uncertainty principle at work. Here we've got these propagators. These propagators involve loop momentum over all energies, but divergences come from the highest energies, so the propagation doesn't go very far at all. So this thing just gives a delta function. So that's a general feature that we'll build on all the time. However, in this case, the log is long distance propagation. You can see that's some function that it's the Fourier transform of log, which I'm not sure what the closed expression for that is. Okay, so at this stage we go back and now let me just do look at the full answer. So we started off with let's take a path integral. It had photons in it, had phi's in it, and it was e to the I the integral d4x is the Lagrangian of phi star, and a. We've done this integral here, and we're left over now with integral dA. So it's still A is still the active field, and I've got e to the I. So let me just call it S effective. Okay, which is now just a functional of A alone. So phi has been integrated out. So this is the process of integrating out phi. And we end up with a couple pieces. We can go back up here and see what they're going to look like. There's going to be a piece that's the divergent piece that's, however, going to be a delta function. So it's going to be f at the same point. That's just like the lowest order Lagrangian. And then there's going to be this log piece left over. So we end up with the one loop effective action. Our one loop effective action is S is integral d4x minus a quarter f mu nu. And then there's one from lowest order plus a divergent piece, which is, I'll just call it Z3 minus 1. This is the 1 plus 1/12 1 over 16 pi squared 1 over epsilon bar piece. Okay. Actually, there's truth in advertising. I'm dropping a one little constant. Actually, it goes into Z, but if you know about evaluating dimensional regularizations, 1 over epsilon times 1 over d minus 3 is not just 1 over, so it's d minus 1, is not just 1 over 3 epsilon. There's also a finite piece left over. It's probably a third. I'm not doing this in my head well, but there's a finite piece left over there. I'm just dropping that. I'm going to drop it in a formula that I have later on also. Just let's not worry about it. Okay, and then I get an additional piece, which is integral d4x, d4y, f mu nu of x, this L of minus y, f mu nu of y, a true non-local piece. This guy, sometimes you can see written in the following suggestive notation: d4x f mu nu log box over mu squared f mu nu. And actually, I've forgotten a couple constants here. There's just write it as be squared. B is this 1/12 with 16 pi squared, and e squared is there. This actually is the beta function of QED for a scalar, because this log box is the running of the coupling constant. At this stage, we do renormalization here, so we define renormalized fields. A mu renormalized is the bare A times Z3 to the minus a half. And I now have the renormalized one loop effective action. And the way you'd use this is this gives you your usual propagators now fully renormalized. So I would do exchange like that. This one gives me a log q squared correction when I'm in momentum space. So I would just do this, and this is the log q squared piece. And I get the same thing that I would have gotten from doing the whole Feynman diagram calculation before. Okay, if I'd had in some sense, I've just done something in a different way now by taking the field in this formalism as a background field, and then doing the integral, and then afterwards expanding. So I'm now going to use this by expanding afterwards. I've just really reversed the usual order of doing things. A couple of comments. So QED, this has not bought us much. QED is simple, so I could do it the other way. So not much has been gained. However, I've done renormalization directly in the action. And I know from having explained wave function renormalization in field theory class that there's always this sort of an awkward moment when you're trying to explain wave function renormalization. It's not the easy, mass renormalization is easier to explain. Some of you guys know I've done this. This one here is pretty obvious here. Having done it this way, it's clear that you want to renormalize your fields to get rid of that piece. So it's actually more obvious and more logical to do it this way. It's also a simple way to see the result. This is F mu nu. You see it's gauge invariant. You're not taking matrix elements yet. On box, you can see the running of the coupling constant if you work a little bit harder. And this could be done for other things. So for example, let me imagine doing a massive field. I was doing masses here mainly just to get rid of a few diagrams. But I would, the piece that goes like d4x f log box f would turn into now integral d4x f mu nu box over m squared with some coefficient, some number f mu nu. This comes from just doing the expansion that in the vacuum polarization, when you're doing vacuum polarization, you get a piece that goes like q squared over m squared instead of the log when you're at low energies. Okay. Let's just do some terminology now. This includes the one loop effects. It's higher order than we normally allow in renormalizable field theories. This is what you would call an effective Lagrangian. It's 1 over m squared. So I've integrated out a heavy field. So when we're doing effective field theory, this is an example of how you get local effective Lagrangians. This is also local. because this guy was heavy. So it's again the uncertainty principle, removing something that's massive, you get something that's local. This guy here, I labeled it above the effective action. Yes, terminology, when you say effective action, you don't necessarily imply locality. Effective Lagrangian, you imply locality because a Lagrangian is a local object. Effective action, you don't imply locality. This particular one is non-local. And that's because it's the effect of massless particles. So the uncertainty principle again says that you can't localize the effects of massless particles. Their divergent structure is local, but their low energy propagation is non-local. So we've seen some of the principles of effective field theory in this calculation also. Last thing I have noted down to say is I've inadvertently also shown you something that's called the Pastarino-Velopment reduction. Let me just explain what Pastarino-Velopment reduction is. If you remember, when you start off doing these Feynman rules, you have momentum factors inside the loop integrals. So if you imagine doing the loop of vacuum polarization, you have got momentum factors there. And I did this bunch of integration by parts, pulling it in and out of the integrals, and put all the momentum factors acting on the fields on the outside. And I reduced it down to what's called the scalar bubble diagram. So this is just this picture here. It's a bubble, but with no momentum factors in it. Okay, so this is an example of Pastarino-Velopment. Reduction, which basically says that you can take all one loop Feynman diagrams and reduce them to scalar loop integrals. So I did this to the scalar bubble. But there are some triangles and box, but it stops there. At one loop, you get all your integrals, even no matter how many legs in it. You know, you have 13 propagators in it at one loop. It all goes down to scalar bubble triangles and boxes. It's actually a very powerful theorem. It's also very painful to prove if you ever try to do it. But the interesting feature is that it goes to scalar. Scalar integrals are easier to do than ones with lots of momentum factors in them. And so you can write a computer program that takes an arbitrary diagram and reduces it to these guys, and then you know the answer. And that's basically what I did. I did the Pastarino-Velopment reduction to take integrals that had momentum factors in it into the scalar bubble. I only needed a bubble here because I started with a bubble. Okay, so that's just an aside note, but it's sort of, if you've never seen that before, it's actually sort of interesting. Okay. So that was the background calculation. I want to generalize it now, but do anyone have questions before I go on? Right. Okay, so let me generalize. Let me do lots of different theories all at one time. Okay? And then I'll do a very explicit example that's very, very non-trivial. So let's just take a Lagrangian that's phi star. I'm going to write it as d mu plus sigma of x phi. Okay. Now, in this notation here, these phi's could be lots of components, could be lots of stuff. So it could be phi 1, phi 2, however many you have there. So let's just take a bunch of scalar fields. Sigma could have a constant in it, so these guys could all be matrices in this basis of phi's. Sigma could have a mass, be masses terms. So if I just took it to be a mass matrix, the diagonal elements of it would be a mass matrix. And D, I'm going to take to be, so d mu is d mu plus gamma mu. Okay, and again, the gamma mu can be matrices. So I'm being pretty general here. The result, well, we've sort of done it all already. We did the gamma mu case. The sigma case is really, really easy to imagine how we did it. Remember, we ended up with log, well, in this case, it'd be log d mu plus sigma. And we wrote that as log box 0, just the derivative part, plus we had d mu gamma plus gamma d mu. Now we'll have a sigma piece there. Oh, there's a gamma squared piece. And we factored out, so log box 0, 1 plus 1 over box d gamma squared plus sigma. And then we expand it. Okay, well, we've already done the d gamma pieces. That's just the same work I just called with A before. The sigma piece is very easy. When you see the answer, you'll see it's obvious. You're expanding to second order. You have a 1/2 when you expand the log. So log 1 plus x has that 1/2 x squared. You'll see that 1/2 here. And then you just get, since that's a scalar, you get a scalar propagator. So you get, here's the answer. The change in S from doing that is integral d for x, d for y. There's a trace if these guys are matrices, so I still have the residual trace over the matrix indices. Then I end up with gamma mu nu of x. I get my same old thing, del squared Feynman propagator of x minus y over 4 d minus 1 gamma mu nu at y. And then there's a sigma piece. It's just plain old, the propagator with nothing else. It's the scalar propagator squared, because that was a scalar.
Are the gamma mu's anti-symmetric derivatives the gamma mu's?
Is that a question?
Yeah, what are the gamma mu's?
Okay, I was about to say that. Gamma mu nu.
Is that the anti-symmetric?
Gamma mu nu is the d mu commuted with d nu. So it's what we had as f mu nu before, because that's the way you defined f mu nu. Here, So in doing this one, I mean, I'm probably exaggerating how easy it is. It takes a little extra work, but the 1/2 sigma del squared sigma is pretty obvious just from expanding this formal notation right there. The piece that you have to do a little work on is if these guys are matrices. This part I already did. So this is the F mu nu that we already did. Sorry, gamma mu. The piece that you have to do a little extra work, gamma mu, gamma nu, minus gamma nu, gamma mu. If these guys don't commute, if they really are matrices, you have to do some work to get that. And you have to do a little work that shows the cross term vanishes. There's a gamma times sigma piece that comes back. We'll see it a little bit later, but it doesn't enter this. In this case, the gamma sigma piece is a total derivative because there's the derivatives on gamma. I don't know. That's you can see. So if you want to see this worked out in a little more detail, you can do that Gasser-Leutwiler paper. They do this in matrix notation there. I will show you the answer that comes out of Gasser-Leutwiler. But here we've got something that's now we've taken this more general theory and we can renormalize this one pretty easily. So the divergences are local, like we did before. So the part of the action that's divergent is integral d4x I over 16 pi squared. It's 1 over this epsilon bar times, well, this first piece gives me 1/12 gamma mu nu, gamma mu nu, plus 1/2 sigma. So any theory that has, you can just read off the divergences without doing any calculation. You just have to take whatever gamma is there, whatever sigma is there, and you've got your divergence structure calculated once and for all. You also get the associated logs. Okay, so that's fine. So we've done many theories all at once here. What don't you get in what I've done so far is you don't get triangles or boxes. So if there's a triangle diagram or a box diagram, you don't get those. But these guys, if you know anything about triangle diagrams or box diagrams, there's this loop integral is d4L, and there's 3 propagators there. So this guy goes like integral d4L over L to the 6th. So this one has L to the 8th. These are finite in the ultraviolet. Okay. I mean, you can get those guys also, but they're all going to be finite, so they're not going to contribute to divergences. So amazingly enough, you've got all your divergences of your general theory. You get the logs from doing this to get the the low energy parts of these other diagrams, you'd have to do them also. Okay. So now let's do, so there's my generalization, and now I'm going to do a very, very non-trivial calculation. Anybody want to ask? Okay, so here's a, okay, so basically what I'm going to do is I'm going to show you chiral perturbation theory. The reason for doing this is that this works very much like gravity. I'm going to take a nonlinear, non-renormalizable theory and do all the loop diagrams that one needs. So let me just tell you what the theory is, and then we'll say some more words about what it is, how to do it. So the Lagrangian that I'm going to start with is going to be written in the following formula. It's going to be a theory of pions, photons, interacting with W's, whatever, weak interactions or electromagnetic interactions of pions. I'm going to do F squared over 4 trace d mu u u dagger, okay, where u is e to the I tau dot pi over f. Okay, let's slow down a little bit and say what that is here. So tau I are the 2 by 2 Pauli matrices. Pi I is pi 1, pi 2, pi 3. So 2 by 2 Pauli matrices, there are 3 of them, 1, 2, and 3. These are the pion fields, so these can be broken up into pi plus and minus is 1 over square root of 2, pi 1 plus I pi 2. Pi 3 is pi 0. So this is describing interactions of pions, but the really odd thing about it is that it involves the exponential of this matrix. So if you start this thing out here, this starts off as d mu pi I, d mu pi I, but there's an infinite number of terms when I expand that out. Okay, the normalization is chosen this f there and that f taken to be the same, so that when I do this, I take the trace, I get the usual kinetic energy piece, but then I have a bunch of interaction pieces there. Okay, this also could be used in SU3. In SU3, you add the kaons and the eta, and this then u is e to the I lambda dot phi over f, where lambda are the Gelman matrices, and phi are the octet of
Pi d mu pi terms. Is that the same way that you write Galileans? Because you're mixing kinetic terms with field.
Is there a question there? Or?
No, just those extra terms. They're like you're mixing fields with kinetic kinetic terms with the fields.
Yeah, so the interactions all have 2 derivatives.
Right.
That's actually interesting. It's so the first term I actually don't. I think I'm doing this from strict memory, but I think it's 1 over 6 f squared. Pi dot pi d mu pi d mu pi.
Don't Galileans kind of look like that?
Well, these are Goldstone bosons, so that's a very common form to have when you have Goldstone bosons. Goldstone bosons end up always with derivative interactions. So I don't know. Going from memory, that's what the interactions look like to start off. There's 2 derivatives on the field. But this is going to be just like our analogy for gravity when we're doing it, because remember the action R has 2 derivatives in it, and it has, because their indices are raised and lower, it has large numbers of G's. So if I am looking at derivatives acting on G's, all the interaction terms in the Einstein action are 2 derivatives acting on the fields. And there'll be an infinite number of terms in that one also. So that's why this is a nice analogy. Okay. For my purposes, I don't need you to know where this comes from. Actually, I'll derive it later in the course when we're doing effective field theory. I'll derive it from a renormalizable field theory. But for now, it's just, for me, it's important that it's a complicated interactions of these fields. Let me just tell you a few more things about it. This d mu u is the usual derivative acting on the fields, but then you can also have interactions with gauge fields. So L u minus u r mu. These guys can be matrices, since this is in SU2 or SU3. And so if I wanted to do QED, I would take L mu equals R mu is equal to E times the charge matrix times A mu. So charged particles interact. That's why the charge matrix is there. If I wanted to do the weak interactions, I would set R mu equal to 0, so the weak interactions are only left-handed. I take L mu to be, if I want the charge W, I just take it to be tau plus W mu. Tau plus is the charge raising operator. So that's this Lagrangian has a particular symmetry. It has an it has this U matrix can be transformed with a matrix, different set of matrices on its left and right. And the L is correspondingly transformed by L mu L dagger. R is transformed by R mu R dagger. So if you just look at this, you can see there's an invariance of the covariant derivative of the Lagrangian as a whole. So this is an SU2 left cross SU2 right, or SU3 left cross SU2 right symmetry. It exists in physics because the QCD has this symmetry approximately. So this is the theory of pions, and the one thing I am simplifying is here is I'm setting the pion mass equals to 0, just because there's no point carrying it along. I mean, I could put it in. It's easy to put in. It's in the book. You see it in the book. But so this is a theory that goes by the name of chiral perturbation theory. And if you want to do the interactions of pions and kaons and photons, you calculate away. Basically, so the usual way you do this, you take some process you want to do. Let's imagine I want to do k goes to pi e nu. Okay, I would say, well, I need to do a W interaction, so I would use this thing to get my W there, and here's a K pi. I can expand that out, but I want to do this to one loop, so I would also then do interactions that took pi's into pi. I would write out vertices that look like this. I'm sorry. 2 extra fields there. There's a bunch of diagrams I can do, and I would then end up calculating away, doing things like this. So here's K, pi. There's also all right, there's a bunch of diagrams. There's this guy, that loop, etc. So I'd do all the loop diagrams. I'd find the divergent. I'd figure out how I was going to renormalize this. I then do that process, find out the renormalized result. Okay. And then I want to start up another process. Okay, I might want to do, pi goes to pi plus goes to pi 0 e minus, and I would write out all the diagrams from that and draw them up. Renormalize that diagram process, keep going. Okay, doing it process by process. What I'm going to do for you now is I'm going to do every diagram in chiral perturbation theory all at once. Okay, I'm going to do it all by doing this background field method. So background field, this is the next wrinkle in background field method. Previously, the one I did, I was integrating out a whole field. The whole field phi was integrated out, and the background field was A. Here, I'm going to allow the pions to be both the fluctuations, the quantum fluctuations that go into the loop, and the background field at the same time. So in general, if you're doing background field in general, the way you do it is you write the full field as some background field plus a fluctuation. Okay. The Lagrangian then gets written as the Lagrangian involving the background field plus there's an L prime of phi bar times delta phi, and then there's a delta phi some operator delta phi piece. Okay, this first piece vanishes by the equations of motion. So that's what you know is the first variation of the Lagrangian equals 0 by Euler-Lagrange equations. So the first variation that you're going to find is this one that has 2 phi's with some differential operator here. You can then do the loops of delta phi's, and you get the 1 over determinant of the operator again, and we then play our tricks with that. Okay. We're going to be able to put this almost always into the form d mu plus sigma, because there's not much else you can do. And therefore we've done the loop integral for this. So let me just carry this out for you in the case of the chiral perturbation theory. So what we're going to do here is we're going to expand U into a background field and a fluctuation. Okay, so here I'm going to call it U bar and e to the I delta. Okay, delta is going to be in the 2 by 2 case. It's going to be a tau I delta I. I've put it in this form because this is a unitary matrix. This keeps it a unitary matrix, and I can keep the symmetry properties. Let me save the symmetry properties to talk about as I get to the end. But what I've done is I've got the background field, I've got my fluctuating field delta. The goal then is you expand the Lagrangian. The action then is integral d4x Lagrangian of u bar. The first term vanishes by the equations of motion, and then the second piece is f squared over 2 delta a some d mu plus sigma a b delta b, and then I stop at that point there. Now it's a little bit of algebra, but it's not that bad. I have clipped the answer down here. Here's the answer. Let's copy that. Move it up. Now, for our purposes here, you're supposed to neglect that piece there, because that's the math terms which I'm dropping, and I don't want to teach you the notation. But basically, and I've done it for SU3 here, and there's the U bars, in the left and right-handed fields, and I basically just have covariant derivatives. Okay, so I mean, in some ways, this one is pretty easy to see. You just had a pion, and here's my 2 covariant derivatives that were there. Anyway, it's somewhat easy. But then, all right, while I'm down here, let's get another one. But then I now know the divergences. So the divergences then are delta S divergent is this integral d4x trace. Well, I I had written down it's 1/12 gamma mu nu, and 1/2 was sigma times sigma squared of x. The piece I just copied is the gamma mu. You could just work out what it is. Hopefully, I lost it. Yeah. All right. Well, there it is. It's basically just these matrices that we did. I'll move it up for the notes later on, and let's see if I can copy this guy. There we go. Copy. And then it's just a bunch of algebra to do. There we go. Good. Again, there's some things you can neglect here. You can neglect anything, all these terms with these chi's. So we don't need that guy. You don't need that guy, that guy, that guy, or that guy, because this is the massless theory. But we do have these guys here. So these are the divergent parts of the Lagrangian. The way you renormalize, in this case, these are new terms. You have to add terms with 4 derivatives. So you see 1, 2, 3, 4 derivatives there. And there's 2 derivatives in R mu and L mu. Those are just the field strengths formed out of R and L. You have to add terms that look like trace d mu u dagger quantity squared plus ... to the Lagrangian. And so one does that. There's a bunch of terms there. The divergence is then absorbed into the coefficients. It's local into coefficients. Okay, so we now have some new coefficients sitting there in the Lagrangian. This guy is, let's call it L1, some number. But I've renormalized the theory. And then I have leftover predictions. I then have predictions which is the rest of the action. So so we had integral d4x, d4y. We had 1/12 gamma mu. So there's a trace. Gamma mu nu L of x minus y. So one's at x. The other one's at y. Gamma mu nu at y. Plus 1/2 sigma at x, L of x minus y, sigma at y. Okay, so these are, remember, are the logs, the Fourier transform of logs. These are written in terms of the background field, so I probably should have written that as background field. It was correctly done up above. But these logs here are all the logs that you find in the whole theory. So if I want to use this now, that's what to use. I basically just expand gamma mu nu in terms of the fields and sigma in terms of the fields. And I take matrix elements. I don't have to do any more loops. I've done all the loops are done. Okay. So if you think about what we were doing before, or imagine that we were doing this, all these diagrams here are now all done. All these diagrams are done. Every process in chiral perturbation theory has been done. And all I have to do is expand it now. So this is the power of the background field method. The only things I'm missing, so remember I did say there's something missing when I did this. This is only the logs. The first triangle in chiral perturbation theory comes in the following process. There's 2 pi. No one's ever calculated that because no one's ever interested in 6 pion interactions at one loop. So it is, at this stage, it's still missing the triangles and boxes, but in chiral perturbation theory, after the first, the people moved on to 2 loops, but they've never done any triangles or boxes. So this calculation basically includes the first decade of chiral perturbation theory from 1985 to 95. Everybody's work. Most of the time, to be honest, most of the time, you know, I did this. This is part of my life early on too. Most of the time, I would just, you know, take a process and do it because it's not that hard to do. But there are some processes, in particular the one that I wrote up here, the k goes to 2 pi, sorry about this, the k goes to 2 pi e nu, that this was by far the easiest way to do the calculation because there's enough diagrams and enough chances to make minus sign mistakes. This one you don't make minus sign mistakes. You've done everything all at once. It's much easier. Okay, the other feature that I want to share with you about this here is that we have kept the symmetry here. Remember, we had the symmetry U went to L, U, R dagger. Each of these terms has maintained the symmetry. Now, that's completely not obvious at all if you were doing this in process by process. How you knew that you were going to maintain the symmetry, then it was just completely mysterious because you do this process and it's not particularly obvious. You have no way of checking it. But the background field method keeps the symmetry very, very well. So this is why it's also going to be useful in gravity. So basically, when we do the renormalization of gravity, we'll do background field where we'll take a background G mu nu, look at the quantum fluctuations around that, integrate out that, and we'll end up with structures that are still keep the general covariance of the full theory. And if you did it process by process, you never get that. Okay. So okay. let me just start. That's the end of my just background field method by itself. I'm going to do the heat kernel next. Okay. Let me just start that. I have a few minutes. It's worth starting. We'll come back and review it a little bit. In this case, I'm going to do the same calculation once again. I'm going to do this vacuum polarization diagram for photons to start off with. But the funny thing is, this way I will never write down a Feynman diagram. You're not going to have any parameters, with propagators. You don't have to do Wick. Well, I'm going to do a Wick rotation, but not the usual one. You don't do Feynman parameterizations to combine up denominators. You don't do any of that stuff. It's going to be Feynman diagrams without diagrams. Okay, so I want you to follow that as we go through it. All right, so this is a technique that you can't read the gravitational field theory literature without doing it, without knowing it. There's so much is done using this technique. Here's what, let me get the start here. So let's go back to start with trace log. I'll go back to d mu plus m squared. Okay, here actually in this case it's actually easier conceptually to carry the m squared along makes the integrals all look convergent. And so I want to evaluate this. I'm going to use the following. Log b over a is going to be the integral 0 to infinity d tau over tau e to the minus tau a minus e to the minus tau b. Okay, so here's then if I want trace log d mu plus m squared. Okay, let's pull it up here. That's going to be, well, the trace is going to have integral g4x, so we're going to take x as part of the trace. There'll be a real trace also. You have to take this trace also. I have then the integral d tau over tau infinity. And I take x e to the minus tau d mu plus m squared x plus a constant. The constant is like tau a over b. So I'll just take this guy here. That's what I'm interested in. This is the heat kernel. That gives it the name. This is a function of x and tau. And to be honest, there's off-diagonal elements that you see often, sometimes in the literature. You could make it you can make it x h of x prime and tau by just putting x and x prime on the outsides. Slightly generalized it. This one is the trace of the heat kernel is the xx1 summed over x. Okay. So what we want to do then to evaluate this is we have to evaluate that, and that's what I'm going to do next time. I'm going to come back and evaluate the heat kernel. once you've evaluated it, you can do this tau integration, and you're golden. Okay, so we'll reproduce some typical results here, but it's a great way to systematize the type of calculation that we were doing before. Okay, let's stop there. Thanks, everybody.
Thank you.